Dear interstellar traveler, please close your eyes. Let your breath gently synchronize with the heartbeat of Earth. This is a scientific harbor for souls yearning for peaceful sleep. Tonight, let us spread a gentle blanket of knowledge across the vast sea of stars. The sleepy fact you are about to hear are like specks of thought dust drifting in the cosmic depths. Did you know Jupiter continuously plays an infrasound symphony with frequencies 1,000,000 times lower than the human hearing threshold? The pulsar in the Crab Nebula flashes every 33 milliseconds, a cosmic timekeeper more precise than an emerald pocket watch. These relaxing astronomy facts will weave into the most unique, calming space documentary, projecting a personalized space documentary for sleep deep within your consciousness. Listen, this is a countdown from the depths of the universe. In 2025, it began its own farewell ceremony. Its batteries are about to run out. The signal could be interrupted at any moment. 47 years ago, this spacecraft, older than a Nokia, set off carrying the voices of humanity. Now, using its last bits of power, it is sending its final farewell to Earth. It is the Voyager, the loneliest messenger in human history, the one that has traveled the farthest. For the next 50 minutes, perhaps this will be the last time we fully tell its story. August 20th, 1977. These archival shots have long become legendary. On a sunny day at the Cape Canaveral Space Center, a Titan E rocket stood on the launch pad. The moment the countdown ended, it was destined to become the first human spacecraft to reach Uranus and Neptune. This is Voyager 2, a true cosmic odyssey. Ahead lay an unknown journey, traversing billions of miles of cold, dark, empty space. Then, 16 days later, Voyager 1 also launched. Their order of launch hid an important detail, a deliberate part of NASA's plan. The primary goal of their mission was to explore Jupiter and Saturn, their moons, rings, atmospheres, and magnetic fields. Understanding the structure of these gas giants and how they interact with their neighbors was crucial for our understanding of solar system history. These massive outer planets are, in a way, the architects of the solar system. Their enormous mass determines the orbits of millions of celestial bodies, where comets will pass, when an asteroid might fall, or whether it will fall at all. These questions are often decided by them. Their gravity can maintain stability, but if problems arise, it can turn the solar system into a cosmic pool table. Exploring their moons was just as important as exploring the giants themselves. Their work revealed worlds with volcanoes, geysers, subsurface oceans, and even the potential for life. But in the 1970s, scientists knew almost nothing about this. They thought the moons of the gas giants were just frozen rocks covered in craters. The mission's biggest challenge was testing the spacecraft's performance after launch. How long would the systems last? Could they maintain contact after crossing billions of kilometers? This was a monumental challenge humanity had never attempted before. But the day arrived, bringing hours of immense pressure for the mission team. Carried by the Centaur upper stage, Voyager 2 successfully entered the planned Earth orbit, completing the first phase of the launch. Now came the critical phase, a precisely timed burn to send the spacecraft towards Jupiter. If all went well, but trouble arrived. 71 minutes after rocket launch, as the Centaur upper stage began separating from the booster, Suddenly, the Attitude and Articulation Control Subsystem ACS miscalculated, thinking the separation happened too early, causing a loss of attitude awareness. It switched to the backup guidance system. The backup system was like a safe mode with many restrictions. In short, things weren't going according to plan. Fortunately, the Centaur module was equipped with an automatic control mechanism that functioned correctly. In those critical milliseconds, it autonomously corrected the error and stabilized the Attitude just in time for Voyager's separation. Everything seemed to have calmed down, but no one on the team relaxed. It wasn't over yet. The spacecraft still had to leave its parking orbit and head for Jupiter. Just seconds after separation, Voyager ignited its solid-fuel Star 37B engine. The powerful thrust began accelerating the probe. Those 45 seconds felt like a century to the mission team. When the engine shut down, the final speed reached 10 miles per second, and the trajectory was correct. Just as everyone was about to breathe a sigh of relief, trouble came again. Several errors and malfunctions occurred one after another. A protection system, designed to activate only when the probe was far from Earth, was accidentally triggered just hours into the mission. For an hour and a half, the spacecraft struggled to stabilize itself. It used small thruster burns to carefully adjust, eventually pointing its antenna towards Earth. Finally, the onboard algorithm declared Attitude stable. But the most worrying thing still happened. The mission team discovered that a platform carrying specific instruments indicated it had not deployed correctly. Remember, if there was a problem now, they couldn't chase after it to fix it. But luckily, it was a false alarm, just a faulty sensor acting up. Eventually, all issues were resolved. Time moved forward to weeks to September 5, 1977. The same launch site, the same type of rocket, carrying an almost identical probe. Voyager 1 was ready for launch. With the experience from Voyager 2, this should have been a routine launch mission. But another unexpected event occurred. After the Titan I rocket lifted off, its second stage LR-91 engine shut down prematurely. Only the final Centaur booster could save the mission, as the Centaur's fuel tank was down to just 3.4 seconds of propellant. Voyager 1 finally successfully entered orbit after operating smoothly for 2 weeks. On September 18, 1977, just 13 days after launch, engineers commanded Voyager 1 to turn its camera platform towards Earth. The camera lens happened to capture Earth and the Moon in the same frame, thus the first image in history to show both Earth and the Moon simultaneously was born. They also comprehensively tested the cameras and other key systems. Finally, engineers took a series of images, 18 different angles in total, each shot through red, green, and blue filters, resulting in 54 frames. Since the antenna wasn't firmly locked on Earth yet, the data was saved to onboard memory. It wasn't until October 7th and 10th, 1977, that this data was transmitted to Earth. This wasn't like today's smartphones where a selfie is sent back and viewable instantly. NASA needed months to process and verify the data before it could be presented. Remember the beginning, where we said Voyager 1 launched later, but something magical happened on December 15, 1977. Voyager 1 about 106 million miles from Earth, overtook Voyager 2. Wasn't it launched later? How did it overtake? The answer is simple. Their missions and flight paths were different. Voyager 2 launched first, but it took a more winding path. Voyager 1 took a straighter trajectory, and these routes weren't achieved by stepping on the gas, but by the planets themselves. What we often call planetary gravity assist. The idea of visiting all four outer planets came from the structure of the solar system itself. This concept originated in 1965 when Michael Minovich at the University of California made a breakthrough discovery. He mathematically proved that a spacecraft could use a planet's gravity for acceleration without burning fuel. Then his colleague, Gary Flandreau, noticed the urgency of this. It was a once-in-a-lifetime launch opportunity. Such an alignment of planetary orbits occurs only once every 176 years. Yes, every 176 years, the outer planets align in a rare configuration, allowing a series of gravity assist maneuvers. The spacecraft would pass very close to a planet, almost tangentially and at high speed. If done precisely, the planet's gravity acts like a slingshot. If approaching Jupiter on the correct trajectory, Jupiter's gravity would grab the spacecraft and fling it away like a slingshot. Imagine throwing a ball at an oncoming truck. The ball bounces back much faster. The same happens with the spacecraft. It flies past the planet and gains orbital energy, using almost no fuel. It's just physics and extremely precise calculations. Then the spacecraft flies to the next planet, repeating this trick again and again for times in total: Jupiter, Saturn, Uranus, Neptune. And precisely in 1977, a spacecraft could fly by Jupiter, then to Saturn, then to Uranus, and finally to Neptune, all in sequence. Voyager 2's flight path was launch into a heliocentric orbit, fly by Jupiter, and use a gravity assist to turn its path towards Saturn, near Saturn. Use another gravity assist to adjust its orbit and turn towards Uranus. Then perform another maneuver at Uranus, tilting the orbit slightly towards Neptune. Finally, fly by Neptune's pole, using its immense gravity assist to dive 48 degrees below the ecliptic plane. After Neptune, no more maneuvers. Voyager 2 continued on its path out of the solar system. Voyager 1's trajectory was launch into a heliocentric orbit, fly by Jupiter, use a gravity assist to turn its orbit towards Saturn, near Saturn and Titan. Perform a dual gravity assist, kicking its orbit sharply upward to 35 degrees above the ecliptic plane after Saturn. No major gravity assists. Voyager 1 thus left the solar system. You might think this trajectory design was just to save fuel. Not entirely. Its significance is greater. Each gravity assist not only accelerated the spacecraft, but also changed its course. One could say without these gravity slingshots, the spacecraft couldn't navigate so deftly. The engine power and fuel were far insufficient for such performance. With these boosts, Voyager to reach Neptune in just 12 years. Without them, the journey would have taken 25 to 30 years. And this was that crucial 176-year opportunity. It was a gamble. If it failed, the next chance wouldn't come until 2152. Fortunately, they succeeded. No second chance was needed. Despite the challenges after launch, both spacecraft steadily headed towards Jupiter. On January 10, 1978, NASA released this epoch-making image. It was the first image ever taken by a spacecraft showing Earth and the Moon in the same frame. At the JPL lab, they processed these images. 3 black and white frames, each passed through red, green, and blue filters, then combined into a full-color image. But that wasn't enough. The Moon was much darker than Earth, so its brightness was triple to prevent it from disappearing in the picture. The very existence of this photo confirmed that Voyager 1's camera and data storage systems were working correctly and ready for future achievements. And these achievements, even from a 2025 perspective, are hard to comprehend how they were accomplished in that era. Back then, there were no space shuttles, no International Space Station, no Mars program. The internet didn't exist. GPS didn't exist. Mobile phones didn't exist. People wrote letters to each other on paper with stamps. It was a completely different world, a completely different century. So how were the Voyagers built in that era? They were designed as science stations, equipped with cameras, spectrometers, magnetometers, etc. The Voyagers had to collect vast amounts of data, record it, transmit it to Earth, receive new commands, and do so for years across unprecedented distances. Even by today's standards, it was an unprecedented space mission. In 1972, NASA approved a new project named Mariner Jupiter-Saturn 1977. It wasn't until 5 years later that the mission received its iconic name, Voyager. The intense development of the spacecraft began then. John Cassani was responsible for the project's engineering aspects. Edward Stone became the science director. For reliability, most systems were duplicated, including computers and navigation units. In fact, from the beginning, NASA decided to build 2 identical spacecraft so they could serve as backups for each other. If one had a problem, the other could continue the mission, at least partially. Engineers often manually tested individual components for maximum reliability because once launched, there was no chance for repairs. And this mission was expected to last decades with many complex maneuvers ahead. So what kind of machine could accomplish such a feat? Each Voyager has a sealed boss, a 10-sided prism shape, 0.5 meter high and 1.8 meters wide. Mounted on top is a 3.7 meter diameter high-gain antenna for communicating with Earth. There are also thrusters, nuclear batteries, radiators, and deployable booms for mounting scientific instruments. Without fuel, it weighs over 720 kilograms, about as tall as an adult, but visually feels larger due to the huge dish antenna. This antenna is the spacecraft's ears and mouth. Everything it hears from space and everything we hear from it goes through this big dish. Now, let's talk about something that sounds like a joke today. The spacecraft was controlled by 3 independent computers, with total memory adding up to about 68 kilobytes. In 2025, you might need a moment to grasp how small that number is. Your phone memory is often several GB, even tens of GB. 1 gigabyte equals 1 million kilobytes, meaning your phone's memory is hundreds of thousands of times larger than the total sum of all Voyager's computers. All navigation, telemetry, data system control ran on this memory, smaller than your social media profile picture file. Today, perhaps the memory in your smart rice cooker is larger than that era's spacecraft. It's mind-boggling to think about. Voyager also had data storage, like a hard drive to save important data on board, like a USB drive today. Except in 1977, that USB drive was a tape recorder with a capacity of 67 megabytes. That could store at most about 100 camera photos. These photos were stored on the tape, waiting for an opportunity to be sent back to Earth. But it's important to mention, without ground stations, the Voyagers would be scrap metal. And the farther they flew, the more critical the ground stations became. By April 1978, Voyager 1 had traveled an astounding 160 million kilometers from Earth. This was both good and bad news. Good news, it was getting closer to Jupiter. Bad news, the communication signal was getting weaker, but this was expected. The spacecraft successfully took the first black and white test photos of the gas giant and began transmitting them to Earth. Then it started taking a photo every 96 seconds for 60 Jovian days, which is 25 Earth days. These photos were later made into a time-lapse zoom video. The quality of those images was a bit like black and white silent films from the Chaplin era. But even so, it was far better than what the best telescopes on Earth could see at the time. Even with such a weak signal, radio waves travel at light speed. The greater the distance, the bigger the problem. Every command sent from Earth took 15 minutes to reach the spacecraft. For perspective, a signal to the moon takes only 1.5 seconds, so every command was like playing space ping pong. Earth sends a command, waits 15 minutes for it to arrive. This meant that even at the first mission destination, Earth had to wait half an hour to get any requested reply. Jupiter was just that far. If distance was one challenge, signal strength was another. The signal from Voyager relied on its own transmitter. Its power ... here, you really must pause and appreciate this, was only 23 watts. You heard right, not kilowatts, just 23 watts. A common incandescent light bulb has more power than the transmitter of a spacecraft flying to Jupiter and beyond. It sounds strange, but that's the reality of deep space missions, any higher power, and the spacecraft simply couldn't supply the electricity. So this faint signal had to be captured and decoded perfectly with no errors. Scientists spent years making this possible, while engineers assembled the Voyager prototypes. Equally important things were happening in 3 remote corners of Earth. Goldstone in California, the mountains near Madrid, Spain, and Tidbinbilla Valley near Canberra, Australia. These 3 distant locations together formed a system, the Deep Space Network DSN. The site selection was deliberate, ensuring that no matter how Earth rotated, at least one station could maintain line-of-sight contact with the spacecraft. Around that time, JPL formally approved a modernization of the entire network. Engineers upgraded old dish antennas and equipment, some used during the Apollo missions. But for Voyager, they needed something bigger and more complex. By 1977, each DSN station had a massive 64-meter antenna and a few smaller 26-meter antennas left from the 60s. Scientists planned to add new, more powerful 34-meter antennas. The old 64-meter antennas were to be expanded by adding a rim, enlarging them to 70 meters. The heart of these antennas was special signal receivers, ruby masers. These are similar to lasers, but deal with radio waves instead of light. They act like supersensitive microphones because they operate near absolute zero temperature. This was the only way to reduce noise to unprecedented levels. The stations were made extremely sensitive, needing to hear the faint signal from hundreds of millions of kilometers away. That almost inaudible 23-watt transmitter was expected to send data back to Earth continuously for decades, and that data was everything the Voyagers could detect with the best instruments of their time. The Voyagers were equipped with state-of-the-art instruments for their era: camera systems, infrared spectrometers, radiometers, magnetometers, plasma spectrometers, etc. Each spacecraft had 11 instruments in total. It's no exaggeration to say its cameras were masterpieces of engineering at the time. They included two separate modules, a narrow-angle and a wide-angle camera. The narrow-angle camera was like a telescope for capturing details of moon and planet surfaces. The wide-angle camera was for panoramas, ring systems, and global atmospheric images. By today's standards, 800 by 800 pixel resolution is modest, but in 1977, it was top tier. The cameras could also take pictures through various filters, from ultraviolet to near-infrared. One filter was tuned to the so-called methane absorption band. This wasn't a stripe in the image, but a very narrow wavelength range where methane absorbs light particularly strongly. This allowed scientists to see things invisible in normal light: cloud layers, atmospheric structures, even differences in chemical composition. Almost all instruments were mounted on a special rotatable platform, one of the key engineering innovations. This allowed Voyager to multitask, observe while flying past a planet, while always keeping its antenna precisely pointed at Earth. But the biggest challenge was power. Solar panels were useless. Sunlight was to weaken the outer solar system, so they designed a more reliable solution for Voyager. Each spacecraft carried 3 radioisotope thermoelectric generators, RTGs, nuclear batteries. These convert radiation indirectly into electricity. Each unit contained 24 small pellets of plutonium-238 dioxide, weighing for 0.5 kilograms total. As the plutonium decays, it releases heat, which is converted into electricity. Here's an interesting figure. Over 48 years, each Voyager spacecraft generated about 150 megawatt-hours of electricity. What does that mean? Enough to charge a smartphone 11 million times, or on an average refrigerator, for about 300 years. Sounds impressive, but remember, it powered computers with memory smaller than a car key fob, a transmitter weaker than a baby monitor, and a hard drive that was magnetic tape. From today's perspective, it's hard to believe this thing could fly anywhere, yet, even then, Voyager never stopped creating miracles. On September 8, 1978, Voyager 1 left the asteroid belt between Mars and Jupiter. On October 21st, Voyager 2 followed. This phase was considered quite dangerous. After all, it was the asteroid belt, but few on the team doubted they would pass through. because two other twin spacecraft had already paved the way before. Yes, Voyager had predecessors. On March 2nd, 1972, 5 years before the Voyager mission, an Atlas Centaur rocket launched from Cape Canaveral, sending the Pioneer 10 spacecraft into space. A year later, its twin, Pioneer 11, set off. They became the first explorers to reach Jupiter and Saturn. It was somewhat like a reconnaissance mission. The Pioneer's goal was to scout the path, see if they could pass through the asteroid belt unscathed. Voyager was prepared for a much larger, more complex expedition. In a sense, Pioneer paved the way for them. Now we know you can fly directly through the asteroid belt without hitting a single rock. But no one knew that back then, just as no one fully understood how crucial Jupiter's role was in protecting Earth from asteroid threats. Not long ago, space reminded us that those threats are real and sudden. Doomsday could come at any moment without warning. In 1994, the world held its breath watching a terrifying cosmic event unfold in our solar system's backyard. Comet Shoemaker-Levy 9 was heading straight for Jupiter. It was a huge rock, 1.8 kilometers in diameter. It would hit the gas giant, no doubt, but no one knew exactly what would happen. No such event had been observed up close before. What happened next was more spectacular than anyone imagined. As the comet approached, Jupiter's gravity tore it into 21 fragments, each hundreds to thousands of meters in diameter. They slammed into Jupiter one after another like a line of cannonballs. Each impact left massive scars on the gas giant's atmosphere, some even as large as Earth. This is Jupiter. It often takes hits for us, impacts that could have been devastating for us. And part of the Voyager mission was to help fill our knowledge gaps about such space phenomena. By early 1979, a year and a half of waiting, immense effort, and taut nerves finally reached a climax. Scientists were excited, nervous, and full of anticipation as Voyager 1 finally approached Jupiter. On January 6, 1979, the close observation phase began. The spacecraft took the first detailed photos of Jupiter. Soon, it became clear we knew almost nothing about the largest planet in our solar system. Turns out Jupiter has rings not as bright as Saturn's, but who would have thought? This discovery was a complete surprise to scientists, but the biggest leaps were yet to come. 2 months later, on March 5, 1979, 3 flybys in one day change everything. At 12:05 p.m., it reached its closest approach to Jupiter, 350 kilometers from the cloud tops. It was during these days that scientists studied Jupiter's banded atmosphere in unprecedented detail, full of vortices, storms, and wave patterns at belt boundaries. Scientists finally saw the size and shape of the Great Red Spot clearly for the first time, seeing it as a massive, stable vortex with incredibly complex internal structure. At 3:14 p.m., Voyager 1 approached Io, though not the closest approach yet. On March 5th, as it flew into the Jovian system, the spacecraft began transmitting astonishing images back to Earth. Initially, a strange cloud was spotted at Io's limb. At first, they thought the camera was faulty, but soon everyone realized it was a volcano erupting in real time. Later named Peel, it's the largest volcano on Io. It was the first time in human history an active volcano was observed outside Earth. In images processed over the following days, 8 more active volcanoes were discovered. At 6:19 p.m., the spacecraft flew by Europa 730,000 kilometers away. Not particularly close, but close enough for a major discovery. Its surface was found to be almost entirely ice, lacking craters common on other moons. This immediately led to the hypothesis that this ice might be young and unstable. Huge cracks and ridges crisscrossed the surface as if the icy crust had fractured and shifted slightly. No such terrain had been seen before. Since then, the theory of a subsurface ocean has been widely accepted. A sensational discovery, because where there is an ocean, there could be life, or at least a habitable environment. The next day, March 6, 1979, 2 more important flybys occurred. At 2:15 a.m., Voyager 1 flew by Ganymede, 110,000 kilometers away. This moon is larger than Mercury, but has low density. It was found to be about half ice with traces of ancient geological activity. At 5:08 p.m., Voyager 1 flew by Callisto, just 120,000 kilometers from this outermost large moon of Jupiter. It was the first time it was seen in high resolution. Massive craters and ancient, scarred plains, the surface is rich in ice, with signs of a water-rock ice mixture. Callisto proved to be one of the most densely cratered objects in the solar system. There is no geological activity. The surface remains almost as is. Every crater has been preserved for billions of years, like a cosmic museum preserving imprints of ancient violent impacts. On March 13, 1979, Voyager 1 completed its primary observation phase, setting course for Saturn. Meanwhile, Voyager 2 followed almost the same path. On April 24, 1979, it also reached Jupiter and began observations. On August 5, 1979, Voyager 2 completed its Jupiter mission, also setting course for Saturn. But their paths diverged, and not without reason. Scientists had to make a difficult choice even during mission planning. We were initially just a 4-year journey to Jupiter and Saturn. The original mission was planned for only 4 years, covering just Jupiter and Saturn. This limitation was for budget approval, but even so, NASA knew how to plan long-term. Visionary engineers designed the spacecraft trajectory so they could later be directed towards Uranus, Neptune, even Pluto, provided luck held, hardware survived, and the first flybys yielded results worth continuing. However, there was one obstacle: Titan. Titan, one of the most mysterious moons in the solar system, Saturn's second largest moon, and the only moon in the entire solar system with a dense atmosphere, a moon with a truly thick atmosphere. Scientists' curiosity was bursting. What was beneath those clouds? Should they go there? But there was a problem. To get a close look at Titan, Voyager 1 would have to alter its course. This meant it would forever lose the chance to reach Uranus or Neptune. This was the mission's crossroads. 2 options were on the table: either send the spacecraft to Titan, sacrificing the journey to the outer planets Uranus and Neptune, or have it fly directly past Saturn, preserving the possibility of reaching Uranus and Neptune and maybe even Pluto, the team faced a brutal choice: unravel the mystery of Titan's atmosphere here and now, or choose the more distant, later arriving ice giants Uranus and Neptune. One was right there, a sure thing; the other, distant and risky. The decision was made. Voyager 1 would go to Titan, ending its planetary tour after Saturn. Voyager 2 would bypass Titan and continue to Uranus and Neptune. As for Pluto, it would have to wait another 35 years until the New Horizons mission. Thus, Jupiter's gravity provided the necessary boost for the Voyagers. By November 1980, the first spacecraft reached the Saturn system. On November 12th, it came extremely close to Titan, about 6,400 kilometers away. However, Titan ultimately gave a rather unpleasant surprise. Its thick atmosphere made direct observation of the moon's surface impossible. Visible light couldn't penetrate it. Not a single surface photo was captured, but analysis revealed something strange. The surface temperature was near the so-called triple point, where a substance can exist simultaneously as solid, liquid, and gas. Like we see ice, water, and vapor coexist on Earth, but on Titan, that substance wasn't water, but methane. Rivers and lakes of liquid methane, an entire landscape made of hydrocarbons. This spawned the idea for a new mission, a separate, dedicated mission to peek beneath those clouds. Decades later, it evolved into the Cassini mission, but that's another story. The disappointment over Titan's veil didn't last long, because on the same day, Voyager 1 performed its closest flyby of Saturn. The most beautiful planet in the solar system displayed its full splendor before Voyager 1's cameras. The first detailed photos of Saturn's rings were taken. It turned out everything was far more complex than previously thought. What was once thought to be a few dense arcs turned out to be hundreds of ultra-thin rings intertwined, layered with varying shades and structures. A fascinating play of light and shadow on a massive, seemingly delicate celestial body. During the moon flybys, the photos taken by the spacecraft were of such high quality they were almost unbelievable at the time. On November 13, 1980, the spacecraft took a close-up of Mimas. It became a meme before memes were a thing, because of a perfectly positioned crater making it look almost exactly like the Death Star from Star Wars. A coincidence, but surely delighted Star Wars fans. Just one day later, the probe flew past Iapetus, though only from a distance. Its unique color immediately drew attention. Its two hemispheres were starkly different in color. The theory of moons Janus and Epimetheus periodically swapping orbits was confirmed. Nothing similar had been observed anywhere else in the solar system. Long ago, these moons might have been part of a single object. Scientists also discovered something very unusual and gave it a poetic name: shepherd moons. These are tiny moons that herd Saturn's rings, keeping their particles in place, preventing them from drifting away. Their gravity acts like a rein, maintaining order in chaos. This is what the shepherd moon Prometheus looked like. In short, for scientists, Saturn was as much a success as Jupiter. By then, it was time for the two Voyagers to bid farewell forever. After the Saturn system, the Voyagers' paths diverge. Voyager 1 received a powerful gravity assist, essentially jumping out of the ecliptic plane where planets orbit. It raced upward at 16 kilometers per second, becoming the fastest human-made object at the time. As if saying goodbye, the spacecraft rapidly flew past 3 more moons in just 16 hours, Enceladus, Rhea, and Hyperion. Its mission within the solar system was over. From then on, ahead lay an eternal, lonely interstellar voyage. Voyager to remain within the planetary family, continuing its odyssey. Next destination, Uranus. Ahead were years of flight. In January 1986, after 5 years of intense effort by the entire team, Voyager approached the distant, mysterious Uranus. On the way, it discovered something shocking, almost sensational. Uranus wasn't just a distant, dull gas ball. It was different. Its atmosphere, like Jupiter and Saturn, is hydrogen and helium. But beneath it lay an unknown world, a dense, frigid ocean of water, ammonia, and methane. Deeper still, a dark, rocky, icy core. Later, planets like this were classified as ice giants. Uranus also proved to be the coldest of all planets. Even though Neptune is farther from the Sun, it has a very strange, tangled magnetic field, as if Uranus itself wasn't quite sure how to be a planet. In its treasure trove of discoveries, Voyager added several previously unseen rings of Uranus and 10 new moons. And a real surprise, Miranda. It might look like a small rock, but its surface seemed as if someone dumped the entire geology catalog onto it. Canyons, valleys, ridges, fault scarps, as if pieced together from fragments of different worlds. The most striking feature is Verona Rupes, a cliff nearly 20 kilometers high. If you jumped from the top, you'd fall for over 10 minutes. In August 1989, after another 3.5 years of travel, the final act began. The probe approached Neptune, the solar system's final planet. Neptune's atmosphere greeted Voyager with appropriately strong winds and storms. The planet was wrapped in giant storms, including a particularly powerful vortex later named the Great Dark Spot. During its flyby, Voyager discovered 6 previously unknown moons. It also managed a close-up of Neptune's largest moon, Triton. This is an icy world orbiting in the opposite direction to Neptune's rotation. A retrograde orbit, extremely rare. Scientists believe Triton was once a free-floating object in the Kuiper Belt until Neptune captured it, pulling it from its original orbit. Triton's surface is ice volcanoes, liquid nitrogen geysers, plumes up to 8 kilometers high, frozen lakes near the equator, and tectonic features up to 1 kilometer high. It's believed Triton's orbit was altered by tidal forces, its surface repeatedly melting and refreezing. Possibly beneath all that ice, an ocean still exists. One of the most inaccessible oceans in the entire solar system. It was here that Voyager 2 solved one of the oldest astronomical mysteries, the so-called Planet X case, a hypothetical body thought to influence Uranus's orbit. During its Neptune flyby, Voyager 2 measured the planet's mass with unprecedented precision. That single measurement resolved all questions about that phantom planet. Astronomers had once noticed Uranus's orbit behaved oddly, as if influenced by some unseen mass. This led to the discovery of Neptune, whose gravity explained some deviations, but not all. This prompted the search for another, more distant planet. Then Pluto was found, but it soon became clear Pluto's mass was too small, only 1/500th of Earth's, impossible to explain the remaining deviations. Thus, the Planet X hypothesis was born, a massive, undiscovered world beyond the known orbits. It was here Voyager played a key role. It wasn't directly looking for Planet X, but it sent high-precision data on the masses and gravities of the giant planets, particularly Jupiter and Saturn. Considering this data, astronomers recalculated Uranus's orbit and found no anomaly at all. The error that once looked like a hint of an unseen planet turned out to be a calculation error from using inaccurate values. Finally, everything added up. The mysterious Planet X was a ghost. It never existed. After the Neptune flyby, Voyager, who continued on, descending below the ecliptic plane into a region with no specific destination, only darkness, silence, and space. But while Voyager 2 was still sailing between Uranus and Neptune, its older brother was already out. After passing Saturn, most of Voyager 1's scientific instruments were turned off. Only basic environmental sensors remained, just enough to continue observing the cosmos. It seemed the spacecraft was quietly and lonely spending the final phase of its mission. But one person decided this veteran space traveler still had something important to say. That person was Carl Sagan, an astrophysicist, science communicator, and idealist. He proposed an idea that NASA initially didn't take seriously. The idea was simple yet bold. Turn Voyager 1's camera around and take a picture of Earth from nearly 6 billion kilometers away. Scientifically, it had little practical value, but Sagan had a deeper motive: to show how small, lonely, and fragile our planet is. The idea gradually gained support within NASA, but top management hesitated. Sagan persisted. After some brief discussions, the project was approved. Preparations began. First, they had to test if the cameras still worked. Second, they had to devise a shooting plan. This wasn't just one picture of Earth, but a full solar system family portrait, planet by planet, from that distant edge. On February 14, 1990, after 6 months of preparation, Voyager 1 took a series of images. Mars disappeared in the sun's glare. It was too close to the sun to see anything. Mercury was closer. They didn't even dare try, fearing damage from pointing the camera too close to the sun. Pluto was too dim, but the most important photo was taken. In a beam of sunlight, sized at just 0.1 pixels, was our planet, a pale blue dot. This photo was officially named the pale blue dot. Today, this photo is one of the most iconic in astronomical history, not because it's rare, but because it's honest. In his book, the great scientist Carl Sagan described this landmark photo in clear, profound language. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The pale blue dot was the last photo in Voyager program history. After receiving the images, Voyager 1's cameras were turned off again and never turned back on. Voyager 2's cameras were turned off even earlier, after its 1989 Neptune flyby. The next 15 years became a period of near hibernation for the spacecraft. The Voyagers steadily moved away from Earth, periodically sending data back to scientists. Voyager 1 moved upward at about 16 kilometers per second away from the planetary plane. Voyager R2 moved downward at about 14 kilometers per second, slightly slower. Mission funding was threatened several times. As usual, critics pointed to high costs and questioned the value of the return data, but NASA defended the program each time. The team knew the most exciting discoveries were still waiting for them at the edge of the world. On August 25, 2012, Voyager 1 approached the true boundary of the solar system. The scientific community was filled with anticipation. Humanity was about to discover what was on the other side. The solar system has several boundaries, or rather things scientists agree to define as boundaries. The nearest boundary is Neptune's orbit, the last planet. The farthest is the Oort cloud, but there's a third one, far less abstract, a physical, measurable boundary between our planetary family and the rest of outer space. It's called the heliopause, of course. We can't perceive it directly, but it's very real to scientific instruments. This boundary forms a giant bubble around the sun called the heliosphere. This bubble is filled with solar particles, for outnumbering particles from space outside this bubble. The situation is reversed. Galactic particles outnumber solar ones. For a long time, this was purely theoretical. No one knew exactly where the heliopause was, or what would happen when a spacecraft crossed it. In August 2012, theory became fact. Scientists held their breath. Voyager 1's instruments detected a sudden drop in solar particle density and a sharp rise in galactic cosmic rays. The spacecraft had crossed the boundary. It became the first human-made object in history to leave the heliosphere. NASA officially announced the news a year later, in September 2013, after thorough data analysis. 5 years later, Voyager 2 also reached the heliopause slower, but with the same result. In November 2018, it too entered interstellar space. The Voyagers were never designed for this phase of the mission. They were built in the 1970s, originally designed for planetary exploration. By the time they reached interstellar space, many instruments had stopped working. Some were deliberately turned off to save power, others had broken. Yet, even in this state, the spacecraft managed to collect important data. For example, we learned the heliosphere isn't symmetrical. In the northern hemisphere, it bulges outward. In the southern, it curves inward. This changed our understanding of how the solar system interacts with the galactic environment. Voyager even challenged a long-held assumption in the scientific community. Many expected the magnetic field direction. It changed suddenly upon crossing the heliopause, as if the spacecraft would cross a clearly marked line, but that didn't happen. No sudden shift, no wall, but a smooth bending of magnetic field lines gently curving sideways, as if someone quietly repainted the lane markers on the road. It was unexpected and proved that space is far more complex than our models suggested, even in places we thought we understood perfectly. Even after decades, even with half the instruments offline, Voyager continued to make discoveries, not dramatic, but important. The farther they went, the more questions they left behind, but no longer about the universe, but about ourselves. Over time, the Voyager mission began to pose almost philosophical questions to its creators. For example, how do you operate a machine that outlives the people who built it? Nearly half a century has passed. In that time, dozens of parts have been lost, literally. Somewhere, manuals and schematics disappeared. Some things were never written down at all. Many engineering decisions now exist only in the memories of those who made them, and when those people leave, the understanding of why certain things were done one way and not another disappears with them. Sometimes to an absurd degree. In the early 2000s, engineers suddenly discovered Voyager's computers were programmed to shut down in 2010. Just turn off. Why? No one knew. They searched for veteran team members, but no one could remember who added that command or why. But the problem wasn't just the code. It was the people. That was the real challenge. When the project began, it was run by young engineers, many fresh out of university. Today, most of them are in their 80s. They needed to be replaced by people who could work with 1977-era technology. Computers with memory of a few kilobytes, programmed in long-forgotten languages, with hardware architectures so obsolete no one uses them anymore. This wasn't just a technical challenge, it was a lesson. If humanity truly wants to execute missions spanning centuries beyond the solar system, we must learn how to pass our technology through generations and prepare for the most unusual, unexpected scenarios. For example, what if Voyager suddenly started doing something it shouldn't, or began sending NASA messages not in the usual status update, but in an unknown language? Because something similar had happened not long ago, just when the whole world was already on edge. In March 2020, as the world locked down due to the pandemic, the Australian division of the Deep Space Network also went offline. The 70-meter DSS-43 radio telescope, the only antenna capable of contacting Voyager 2, underwent a major upgrade, the first in 30 years. Technicians removed its feed system, replaced actuators, install new amplifiers. The dish now had tens of kilowatts of clean power instead of the old transmitters. Meanwhile, the probe continued sending telemetry data to Earth, but it could no longer receive commands. We could hear it, but it couldn't hear us. The Voyagers are fully autonomous. Each stores its flight plan and memory, occasionally updated via commands from Earth, but the spacecraft always carries basic instructions on board. Still, 7 months of silence is a long time. This 43-year-old spacecraft continued flying, following its preset schedule. But if something went wrong, Earth would be powerless, unable to even offer advice. On October 29, 2020, the moment of truth finally arrived. The upgraded DSS-43 locked onto its target and sent a test command packet. Tens of kilowatts of radio power compressed into a few lines of code. The signal raced through interstellar space for 17 hours. Finally, the Deep Space Network receiver confirmed. Message received and read. Voyager to heard us. It acknowledged receipt, executed the command, and continued reporting. I am still operational, battered by time and galactic storms. The aging spacecraft was still running, but its twin was not. In May 2022, Voyager 1 began behaving abnormally. Telemetry data from its AACS subsystem, the one controlling the antenna pointing at Earth, suddenly became garbled. The signal came through, commands were received, but the data itself was meaningless, as if someone had added a filter or rewrite in the source code. The attitude control system was still working. The antenna was pointing where it should, but the reports sent by AACS looked as if the probe had gone mad. By this time, Voyager 1 was long past the solar system's boundary. These events greatly fueled conspiracy theories. People claimed that outside the solar system was some alien space governed by different physical laws, or that there was no space at all, just some bubble with Earth floating and who knows what void. Perhaps that signal wasn't from Voyager at all. Maybe it was a radio echo, an imprint of some alien medium. But scientists and engineers were more down to earth. They were puzzled by this anomaly for a long time until they found the cause. It turned out the module was sending data through an unused memory buffer, long considered dead. Why? No one knew. They fixed it, but unease remained. These aging machines continue to operate, but each year they become more stubborn. We can no longer confidently predict how they will behave tomorrow. Of course, the Voyagers won't live forever. Their power comes from nuclear batteries. Their lifespan is limited by two main factors. First, the decay itself. Plutonium-238 has a half-life of 87 years. 47 years have passed since launch. Output power has dropped by about 1/3. Second, the degradation of the thermocouples. These devices convert heat to electricity over time. Their efficiency declines today. Voyager's thermocouples can only squeeze out about 220 watts of electricity, half of what it started with. Power loss is about 4 watts per year. Now we are approaching the threshold. On February 25, 2025, mission engineers at NASA's Jet Propulsion Laboratory in Southern California turned off the cosmic ray subsystem on Voyager 1. On March 24th, they turned off the low-energy charge particle instrument on Voyager 2. Each spacecraft now operates only 3 scientific instruments. These measures are part of the ongoing effort to manage the probe's dwindling power supply. Current project manager Suzanne Dodd said, "Since launch, the Voyagers have been deep space rock stars. We want to keep that going as long as possible, but the power is running out. If we don't turn off one instrument on each Voyager now, they might only have a few months of power left. Then we'd have to declare the mission over. The team might maintain contact until around 2030 at most by selectively shutting down systems, but that's it. Then the final scientific instruments will be turned off. Then the transmitters will be turned off. So, around the mission's 50th anniversary, communication with the Voyagers will end. But even that is not the end. The spacecraft will continue flying silently and relentlessly. In 42,000 years, Voyager, who will pass within 1.5 light years of the star Ross 248, in 300,000 years, Voyager 1 will fly past another red dwarf, TYC 31355-1. They will not cease to exist. They will become artifacts, witnesses, ambassadors. Perhaps one day, someone will find them And if that day comes, that someone will find a message inside. When the Voyagers were being designed, someone asked a simple yet bold question. What if someone finds them? Not tomorrow, not in 100 years, but in 1,000,000 years. Even though the chance is almost zero, the possibility is too extraordinary to miss. Carl Sagan's team took this what if seriously. The goal wasn't just to show where we're from, but to try to explain who we are. This is how the Golden Record was born. A gold-plated copper disc attached to each spacecraft. It includes a stylus, a protective cover, and instructions etched directly onto the casing. Inside is a phonograph record containing everything. Greetings in 55 languages, music from various cultures, sounds of Earth, waves, thunder, a baby's cry, a dog's bark, whale songs, a heartbeat, laughter, the sound of a kiss. 3/4 of the record's content is music, from Bach and Beethoven to Senegalese rhythms, Chinese Guqin melodies, Japanese and Peruvian folk tunes. There's blues. There's Chuck Berry's Johnny B. Good. Besides sounds, the record contains 116 images: people, animals, cities, anatomy, DNA, Olympic athletes, a child eating ice cream, a neatly stocked supermarket. All these were encoded as signals and imprinted into the record's grooves. The protective cover has instructions on how to decode it, next to a diagram of a hydrogen atom, a pulsar map showing the sun's location, and instructions on how to play the record. There's even a radioactive timestamp, a thin layer of uranium-238 with a half-life of 4.5 billion years. With this, one could estimate the record's age, provided someone out there has a mass spectrometer and a bit of patience. But there's something else on the record. These images show 27-year-old Andruyan. She was the creative director of the Voyager Interstellar Message Project, responsible for the Golden Record's artistic content, sounds, music, images, and message text. On June 3, 1977, just before the mission launch, scientists recorded her brain activity and encoded it onto that Golden Record. The magic of that moment, and was engaged to Carl Sagan at the time. And as her brain waves were being recorded, she said she was thinking about love. Of course, it's incredibly naive to think someone would understand the meaning of that signal. But the idea itself, to leave a trace of a feeling in the universe, is so profound it makes you feel the romance of humanity. What's next? Earth will continue to listen carefully, devoutly, to the Voyager's gradually fading whispers until around 2030, maybe a little less, maybe a little more, until their cores finally cool down. After that, they will fall silent forever. But the Voyagers will continue their journey now silent, without contact, without power, without destination, but not without meaning. They will drift in the void for millions of years. Perhaps one day, someone will find them, decode the message, and understand its meaning. They will hear greetings in dozens of languages, the sound of waves, a child's laughter, birds singing. They will look at the photos, see mountains, cities, and faces. They will listen to music from Bach to blues. They will think, what a strange, noisy, stubborn, and tenacious civilization this was. A civilization that was always searching, exploring, creating, and always full of curiosity. All right, my friend, let's pause our conversation here tonight. on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.